Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Thank you for joining the ITU AI for Good Biodiversity series. I'm David Thau, WWF's Global Data and Technology Lead Scientist, and I'll be your host for this session. As we better understand the impact that we're having on the Earth's climate, biodiversity, and ecosystems, and feel compelled to mitigate and adapt to those changes, we're constantly faced with the need to prioritize our actions. The range of conservation activities is vast, including creating conservation corridors, addressing wildlife crime, and as part of international agreements, protecting and restoring ecosystems. Typically, any action we take will involve some kind of trade-off. Projects that prioritize carbon sequestration may not address biodiversity loss. Projects that focus on biodiversity may negatively impact local economies. Even within a given type of action, such as restoring degraded land, experts need to prioritize areas for the restoration. Over decades, conservation organizations have leveraged a number of different tools for planning and prioritizing. One of the challenges these tools face is the need for them to adjust to evolving circumstances and to plan for multiple objectives at the same time. And today, I'm happy to welcome Daniele Silvestro, whose work focuses on these issues. Dr. Silvestro is a computational biologist at ETH Zurich and Swiss Institute of Bioinformatics and associate scientist at the University of Gothenburg. His research is focused on the development of new models and software with applications in evolutionary biology, geology, sociology, and conservation biology. His most recent programs include new tools to perform phylogenetic analyses and artificial intelligence approaches to estimate patterns of species richness and guide biodiversity conservation policies. Daniele has authored more than 130 scientific publications across specialized journals like Science, Nature Sustainability, and the Proceedings of the National Academy of Sciences in the US. And he's associate editor for Methods in Ecology and Evolution and Systematic Biology. Dr. Silvestro, it's a great privilege to have you with us today. Please tell us about your work.
Hi, thank you very much, David, and thanks for the invitation, for the opportunity to present our work. I'll be sharing my screen now and talk about some of the recent work we've been doing in our research. Particularly, I would like to talk about biodiversity conservation planning using reinforcement learning. Before we get there, I just wanted to set a little bit the context and I think it is obvious to this audience and to most people around the world that our planet is experiencing very rapid changes that are affecting a number of things, and one of them is biodiversity. Biodiversity is the collection of all living things that inhabit our planet. So if we look at the recent past to understand these evolutionary trends and these biodiversity trends over time, we can analyze using standard statistical methods and unsupervised machine learning. We can analyze the fossil record and how it records extinction events that occurred over time. And what we observed in recent studies is that extinction rates, at least in some organisms, have increased massively over a relatively short amount of time, specifically in just over 60,000 years, which sounds like a lot, but in evolutionary terms is a very short amount of time. Extinction rates in mammals have increased 1,700 times. hundreds of species have gone extinct in the recent past, and causal statistical models have um, identified the human expansion in all of these different facets as one of the main drivers of this biodiversity loss. So it's clear that humans have had in the recent past a negative impact on biodiversity worldwide. But it's also clear that present biodiversity is in trouble right now. So, of course, several species have already gone extinct, and there is very little, if not nothing, that we can do about them. But a lot of species, thankfully, the great majority of species are still around. Yet many of them are endangered right now. So there are hundreds and hundreds of species, thousands of species that are currently threatened with extinction. And so one of the questions that we computational biologists try to address is how can methodological development and computational methods help in tackling biodiversity, this biodiversity crisis? As AI is quickly becoming one of the defining features of our times, how can AI actually help us doing something for biodiversity? In order to understand the priorities and understand in quantify the crisis that biodiversity is experiencing today, we need to quantify and establish which species are actually endangered right now. And the gold standard for evaluating species extinction risks among today living species is the IUCN Red List, which is the red list of the International Union for Conservation of Nature that classifies into simple, discrete categories each species into different degrees of extinction risk, going from least concern all the way to critically endangered. And so this red list is kind of the reference for most conservation action. But to demonstrate one use of AI, we can see how AI can be applied to augment this type of data. So the IUCN Red List covers thousands of species. And if you look at bird diversity, you will find that all of the species have already been assessed by the IUCN Red List. So we can use this tool as a way to quantify which species need conservation most urgently. However, if we look at other organisms, which are even more diverse than vertebrates, we'll see that many of them have not been assessed yet by the IUCN Red List. And that is because it takes a lot of expertise, a lot of time, and a lot of resources to actually go and collect data and assess specifically and manually each of these species. So among the hundreds of thousands of plant species, only about 7% of them are actually assessed. So for only 7% of them do we know if they're threatened with extinction or not. And the numbers are even lower if you look at invertebrates or fungi. At the same time, we do have a lot of data about biodiversity and about human pressure on the environment. So we have a lot of spatial data about occurrence records for hundreds of thousands of species out there. And we can leverage advances in artificial intelligence to parse all of this data and create predictions for extinction risks. So this is something we have been doing over the last few years by using standard supervised deep learning methods to map essentially biological occurrence data along with human footprint and human pressures on environments into predictions of biodiversity risks and species extinction risks. So these tools are available as open source software and can be applied easily to very large data sets. This is an example where we assessed the extinction risks across tens of thousands of tree species worldwide using this supervised deep learning pipeline. This is, of course, not intended as a replacement of the thorough and robust assessment by the IUCN, but it's instead a way to gather quickly good approximations of where extinction risks are and which species may need most conservation efforts right now. Now, we can use these tools to kind of augment the existing knowledge about which species are threatened with extinction, but what do we do then with this information? And how do we actually prioritize conservation actions considering that species don't live in a static environment, but they live in a world that is dynamically changing through land use changes, climate change, and population and natural dynamics. So, given the dynamic state of ecosystems and environments worldwide, we need a tool for optimizing conservation action that is able to actually parse these changes over time and space. And to this aim, we developed a software which we call Captain for conservation area prioritization through artificial intelligence that is powered by a different type of artificial intelligence, not the standard supervised deep learning models, but reinforcement learning. The idea behind the reinforcement learning is that we use a set of AI algorithms that will perform an optimization within a dynamic environment. Here, the dynamic environment will be an ecosystem with all of the species that occur in this ecosystem, but also all other factors that affect ecosystems. For example, climate change, human activities, and socioeconomic factors. This ecosystem, this environment is changing over time and across space, and is being monitored by an agent that is essentially the brain of our AI algorithm. And the agent parses all of this multidimensional data and translates it into conservation actions. This process is optimized through reinforcement learning. The environment is going to look like this, like a collection of species distribution data, conservation status attributed to each species. So we will include in this environment information about which species are threatened with extinction, which ones are not. But it will also include a number of socioeconomic aspects. For example, how much would it cost to protect or restore a certain area? What kind of land use is currently present in each area? And we can provide as well a certain budget that can be allocated for this conservation process. This environment is powered by a simulation of spatially explicit natural processes where species can move around, disperse, reproduce, but also die due to climate change or land use changes. This environment, which is a multidimensional complex environment, is being processed by a deep neural network. This process is basically collecting all of this information and translating it into the next action. There will be the selection of a particular area for conservation or for restoration purposes. The action will have an impact on the environment because it will, for example, reduce the disturbance in a given area because this area is now protected. This will have an impact on our budget, on our land use. It will have a certain cost, but it will ideally also have an impact on the species that live in that area, for example, allowing for the recolonization of a newly restored area. This updated environment is then processed in the next time step by the agent again, which will monitor the environment and will try to understand whether the action that was taken had a good impact, a positive impact on nature or not. So by processing this updated environment and collecting a reward that is essentially a score that the agent gets for every action played in this environment, we will do a round of optimization and the agent will make the next action, this time informed by the previous, by the outcome of the previous actions. So this process, this reinforcement learning process will take place over and over, and like the agent will play this game of protecting nature over and over again, each time updating its parameters. And by the end of this training phase, the agent will have learned how to interpret the multidimensional data that includes species distribution data, land use, costs, and so on, so that it maximizes the outcome of the actions taken. So we can use then a trained model, trained using these simulations to actually produce conservation planning actions that develop over time and as a function of all this multidimensional data. So if we collect then real data with biodiversity distributions and socioeconomic factors, and I will give more practical examples in a moment, we can run them, all of these data through a trained model and obtain a map of conservation priorities. We can use this type of framework because we have this simulated environment. We can use it to make predictions of different types of implementations of conservation policies. And this is, and we can do this even without real data by just simulating different environments, different scenarios, and predicting through our simulations how effective different conservation policies may be. For example, as we know from the landmark agreement from a few years ago, from COP15, many countries worldwide pledged to protect or restore 30% of their area by 2030. This is an extremely ambitious goal that can have extremely positive feedbacks on nature. But of course, it also comes with a lot of challenges. For example, like how well can we plan these conservation and restoration actions so that we obtain the best possible outcomes. And not every 30% will have the same outcome. I mean, this is something we can explore with our simulation using reinforcement learning. So here we simulated a number of realistic data sets where in each data set had like a number of simulated species diversities, extinction risks, but also land uses and costs. And we subjected these simulated environments to different policies, different conservation policies, each of which ended up with a 30% restoration or conservation program at the end. So 30% of these simulated areas were protected by the end of 2030. But the selection of these 30% was modulated in different ways according to different policies. We applied a minimum cost policy that would just look for the cheapest 30% and protect these 30%. We ran models where the 30% was allocated based on biodiversity, so trying to restore or protect the areas with the highest biodiversity. We look at policies where the protected areas were the ones that were the most intact, so the areas that were the least degraded areas. And finally, we ran policies where the selection of the 30% was performed through our reinforcement learning optimized model. Once we run these different policies, we can compare the outcomes of these different policies. So we can look at how much each of these policies cost, how intact the environment at the end of our implementation of the policy is, how much we reduce the threat to species, and how much endangered and critically endangered species were protected by the end of this implementation of the policy. And so in this plots, I'm going to show a relative change compared to a minimum cost policy. So if we take the minimum cost policy as a baseline, we can compare the other policies in relative terms, relative to this benchmark policy. So we calculated, for example, how much each of these other policies would cost relative to a minimum cost policy. And to no surprise, we found that any 30 by 30 policy that is targeting biodiversity in some form by looking at maximum biodiversity, maximum intactness of the environment, or our reinforcement learning optimized policy, any of these policies will cost more than a minimum cost policy. So bottom line is any conservation policy that is targeting biodiversity will be more expensive than a minimum cost policy. On the other hand, we also found that any policy that is targeting biodiversity, it will cost more, but it will also have significantly improved outcomes in terms of biodiversity. So all of the policies, regardless of whether they were AI optimized or naive policies, they will all end up improving the intactness of the environment significantly more than just choosing the cheapest 30%. They will reduce the threats on average of all species, and they will achieve a better protection of biodiversity. Yet, if we optimize these policies using AI, so instead of using some more naive, like metric-based approach, we found that Our reinforcement learning optimized conservation planning was able to achieve the best outcomes in terms of reducing threats overall and increasing the amount of protected range for critically endangered and endangered species. That is, the species that need conservation the most. So simulations are showing that doing this AI approach to conservation planning is actually worth it. Even though it takes more computational efforts, it is actually achieving better results than using more simple and straightforward metrics to guide conservation action. And I wanted to demonstrate this approach in a real case scenario, this ongoing work that we are doing in collaboration with scientists in New Zealand, where we are applying reinforcement learning to optimize the conservation of New Zealand's exclusive economic zone, so in marine environments, within a 30 by 30 scenario. So here we're actually using empirical real data, no longer simulations. And for the specifics of this analysis, we collected spatial and ecological data for over 600 marine species of plants and animals. These are just some examples. So for each of them, we collected and were able to model the spatial distribution, but we are also able to obtain conservation status, telling us which species are currently endangered, which ones are currently least concerned. Because we wanted our simulation, so these are our optimization to be future proof, we need to account for the fact that species geographic distribution today may not necessarily be where the species will live in 100 years from now. And so we wanted to make our optimization future proof in the light of climate change. Based on predictions of future climate change scenarios, we therefore modeled the habitat suitability across all of these species, not only for today, but also how it will change over time in the future. And essentially what we wanted to do in our reinforcement learning optimization is to obtain the best outcomes, not only looking at today, but looking at 100 years from now or 70 years from now. So we generated these habitat suitability maps for the present and for the future. We combined all of this information with socio-economic data because, of course, conservation, if it has to happen in the real world, it will have to account for constraints that occur in the real world. For example, there are some areas where there is ongoing oil and mining efforts, and conserving or restoring these areas may be actually unfeasible. But also, conserving areas may mean that these areas are no longer available for fishing. And so this will come with a certain opportunity cost. So we included catch value, for example, that quantify how much it would mean in terms of opportunity cost to protect a certain area versus another one. Fishing pressure also comes with different disturbances, different levels of disturbances. And we use fishing pressure as mapped for today, but also predicted fishing pressure for the future. We also included marine traffic as, again, a way to measure how much conserving different areas would cost in terms of opportunity costs, but also how much disturbance these may have on the ecosystem. So we put together all of these biodiversity data and socioeconomic data, and we combined it with a predefined set of objectives and targets that we wanted to achieve in our optimization. So we wanted to protect its objectives, we wanted to protect species as much as possible, but giving priority to species that are currently endangered. So trying to protect as much as possible the species that need it most, otherwise are at risk of going extinct. At the same time, we wanted to keep opportunity costs as small as possible. So all else being equal, we want to protect nature, but also minimize opportunity costs, because this will make the conservation action actually more feasible. And our target was to end up with 30% of this EEZ, this exclusive economic zone of New Zealand, protected by 2030. So we combine all of these data along with our objectives and our targets within our reinforcement learning framework and optimize the placement of conservation areas within this context. And so, whereas this data would be really difficult to parse in a standard statistical model because it's so highly dimensional and so dynamic over time, because species move over time, they will adapt to different landscapes and will change depending on how we protect different areas and how we reduce fishing pressures in different areas. So parsing all of these data in a simple statistical model would be very hard to do, whereas within our reinforcement learning framework, we are able to perform this optimization in a dynamic context. And these are the results that we're obtaining so far. This project is still ongoing, so the map may end up changing in the future, but essentially we are able to run this model and identify areas that maximize the outcome in terms of biodiversity protection, minimization of opportunity costs, not only for today, but also for 70 years from now. Through this conservation optimization, we can also see how many species we predict to be still endangered in the future and how this fraction of endangered species may change over time if we apply this conservation policy. So here we started the policy in 2020 and we end up the predictions in 2050. And these are the predicted numbers of endangered or threatened species in the present and how they decrease over time as we protect more and more areas. We see that although we do reach at some point a predicted scenario where we don't have a single threatened species across the 600 that we're looking at, this number of threatened species increases again over time, I think, to some extent. And this is the effect of climate change. Of course, like if species are being pushed away from the area of interest by climate change, then conservation itself is not going to make a difference necessarily, because species will simply no longer be able to live in this area. So we see that for some species, conservation area will not fix it, but for others it will. And if we look at the number of least concerned species, which are the species that are doing well in the ecosystem, we see that we achieve through this conservation implementation, we are achieving a significant increase in number of least concerned species over time. We can also use this multi-objective reinforcement learning approach to optimize for both biodiversity and carbon. For now, I've shown that we can optimize biodiversity outcomes while minimizing opportunity costs. But another question, especially in ecological restoration, is whether we can optimize both biodiversity outcomes and carbon sequestration, because this will address both the climate crisis and the biodiversity crisis. And again, we can use a reinforcement learning framework using multi-objective optimization, where we can explore the trade-offs between protecting with only biodiversity in mind or protecting with only carbon in mind, or something in between. So we can basically assign different weights to different to the rewards assigned to biodiversity and carbon outcomes, and explore how different policies perform along different axes. If we optimize, so these are 5 examples of, and now I'm going back to simulated data for the sake of experimenting with these policies. If we explore different policies where the weight is only given to carbon, only to biodiversity, or something in between, we can optimize all of these policies and see how the predicted priority areas change across space. So these, again, keep in mind that simulated data sets, but what we do see is that climate optimal policy, which is a policy that focuses on carbon sequestration only, will return a distribution of protected areas that is quite different from a policy focused on biodiversity outcomes. So there are certainly some trade-offs that occur when you prioritize for carbon sequestration versus biodiversity conservation. Now we can use this tool to explore the trade-offs, both in terms of which areas we should actually protect under different weights assigned to either carbon or biodiversity, but also trying to predict the different outcomes that we obtain from these policies. So if we look at these five policies going from climate or carbon focused policy to biodiversity policy, we see that, of course, the amount of carbon, these are relative numbers and they're based on simulations again, but we see that, of course, the amount of carbon um, that is accumulated through a climate policy is significantly higher than the amount of carbon sequestered through a biodiversity policy. So there is certainly a trade-off that we observe in terms of how much carbon can be stored under these different restoration policies. But there is also a non-linear trade-off in terms of how much biodiversity improvement we can obtain through these different policies. So this is now looking at relative numbers of species that were threatened at the beginning of the simulation and are no longer threatened after implementing our policy. And you see that the number of species that are no longer threatened after this restoration policy is significantly higher as soon as we start including biodiversity in our optimization. This change seems to be non-linear, so it could be that like even accounting for a little bit of biodiversity outcomes can improve significantly the outcome of the policy in this sense. We could also interpret these types of results in terms of financial tools that can be given to promote different policies. So if restoration is something that can be promoted, for example, by different institutions through carbon credits and biodiversity credits. So if we start to consider a concept of biodiversity credits, and I know there is a whole debate that is probably should be the subject of a different seminar, but there is a whole discussion about what biodiversity credits should be. But if we consider some definition of biodiversity credits, for example, how many species are no longer threatened after the implementation of a policy, so even a simple statistic like this, we could use a bundled biodiversity and carbon crediting system to promote different restoration policies. So to create the financial tools to make these restoration policies financially viable. And we can see that depending on how we value biodiversity credits, we can create policies that are financially viable along this spectrum of going from climate-only policy to biodiversity policy. So if we only consider carbon credits, a climate-oriented policy will be the best in terms of how many carbon credits you can obtain from it. So any biodiversity-oriented policy will have a smaller outcome in terms of how many credits you can collect if we only look at carbon credits. But if you bundle both biodiversity and carbon credits, then you can find ways to actually promote financially policies that don't only look at carbon sequestration, but also allow for biodiversity to be factored in. So we think that this type of tool could be used to explore valuations of biodiversity policies that will make these intermediate policies financially viable. So hopefully this is something that will be explored in the future in the real world. Before I close, I wanted to mention that all of this modeling that I presented so far is very top-down, right? So it's like us running some models, running our AI tools, and then identifying the areas that are best for conserving nature or sequestration of carbon. But it's a very top-down approach. There is no basically involvement of the local communities who are actually the ones that will be implementing the policies and will be benefiting or paying for these policies. So I think it's clear that top-down conservation planning is not the most effective way to actually do conservation. There is increasing scientific evidence for how bottom-up conservation planning, conservation policies actually end up being much more effective, because if there is involvement and engagement of the local communities, this is how you actually get to effective conservation planning. And so one of the things that we have started to develop and work on is an extension of our reinforcement learning framework that actually takes into account this need for a bottom-up conservation planning as well. And we do this through an approach that is called reinforcement learning from human feedback. And this is a type of reinforcement learning that is used commonly in training, for example, large language models. And it's a way you create AI models that ideally will not be as biased as they would be otherwise. And you create AI models that are aligned to specific, to our values, right? Of course, these tools are not perfect, but they're a way to guide AI models so that they align with what we think is right. So the idea that we are starting to explore in our framework is to use reinforcement learning to crunch all of these multidimensional data as I've shown in previous examples, because these would be data that are otherwise really difficult to parse for a single, for an individual person. But then use the outcome of this data-driven optimization in a second step, where we use human feedback, where we engage and consult with local communities to get their take on this AI and data-driven solution. And their take will basically be the basis of a second round of optimization, so fine-tuning of our models, so that which can be repeated over and over until a solution is reached that is both optimal from a data-driven point of view, but also accepted and incorporating the knowledge and the feedback from local communities. So this is a way where we think we can make AI more aligned to what local communities are able and willing to do within their own environments. And we hope that this will make conservation planning more robust and more effective in the future. And I would like to close by saying that artificial intelligence has now become a defining feature of our time, and it's all over the place in scientific research as well. But we should make sure that as we develop new and more powerful AI models, we should make sure that AI is an opportunity and not a barrier. And this is true for within the scientific community. So we need to make sure that AI is not something exclusive to countries that can afford, or institutions that can afford to run these large models and that have the resources and knowledge to run these models. But it needs to be something that is available to the entire scientific community, including from the global south. The tools that we develop need to be available in a very inclusive way. So in this recent paper that we published in Nature Reviews Biodiversity, we outlined some of the ways that we think AI can be made an opportunity for everyone, and not just for the few who can afford to run these very expensive models. Equitable access to AI technologies is one of them, but also the understanding that not all AI models need to be very large models. We can have very small models that are more portable, they have a smaller energetic footprint, and are still maybe equally good for the task at hand. So with this, I would like to close. We have several ongoing projects where we're trying to apply these AI frameworks in the real world, which we hope will lead to some good results for nature and climate. I would like to thank you all for listening, and I will be very happy to take questions. Thank you.
All right. Thank you very much, Daniele. That was great. The work you're doing is amazing, and I like the last few points that you ended with too, the involvement of the bottom-up community input, and also the using different models that are might have different environmental impacts as a great way to close up. Thanks. We have a number of questions from folks, and I'll try to choose among them. There are a lot of them. So let's see. Um, I think, let's see. So one question, here we go from Teddy. And it Yeah, Bex, well, he asks, or Teddy asks, says, this is very valuable work. I have a question. When building simulations like Captain, where the output is a location's conservation priority, how do you validate it? Do you use historical data as ground truth to validate the model outputs, or in general, how are you validating this work?
Yes, it's an excellent question. Obviously, uh, it is difficult to evaluate um, how well a policy will perform in 70 years from now because we need to wait and see, kind of. So we need to come up with a number of metrics that allow us to evaluate um, the solutions that our models come to. So one way to do that is by comparing the predicted outcomes of the policies, the AI optimized policies, against the predicted outcomes of other policies. For example, naive policies like I protect places with a lot of biodiversity, or more sophisticated policies coming from alternative methods to do conservation planning. There are, like, of course, many non-AI approaches to conservation planning, which are they tend to be a little bit more like static in time, but they can still be used to process a lot of data, and they return a conservation priority map. So we can compare, we can benchmark our solutions against, and we did that in several of our papers, benchmark against alternatives. Of course, like the actual outcome of conservation policies depends on very many factors, including, like you protect an area, but then like, is it really protected? How well did the restoration program work? For example, you can plant a lot of trees, but maybe they die the next year because it's not the right trees in the right place, or because of extreme weather. So there are lots of moving parts that are not necessarily easy to predict. But we try to like come up with a number of metrics across which we can evaluate the yeah, how well our models perform. Yeah.
Okay, great. Thanks. Oh, I have a question following up on the bottom-up approach. Are you testing this out yet, or do you have plans for doing that, like getting the community input, and what's your plan there?
So yeah, we started some discussions with scientists in Ghana, in Africa, like to identify areas or priority areas for conservation of plants. This is very preliminary, so we haven't started yet, but we have been discussing this, the idea of running this experiment. So hopefully this will be something that takes place. We are doing this in collaboration with the Kew Gardens, who have been also very active in identifying conservation priorities for plants, um, and with partners in Ghana. So we're ideally we'll get this one started, and if we come up with like a solution and something that worked, then of course we hope that this type of approach will be taken up by other initiatives.
Yeah, it's always very interesting to see where planning exercises land, both with the communities that are implementing and with them, and also just at the top level too. Like getting these feedback loops are always really interesting, and it'll be good to see how the your simulations are interpreted by folks, and yeah,
Yeah,
good.
one
That'd be
important
great.
aspect there, I think, that I forgot to mention is that in the bottom up take, like you will also include things that are otherwise really difficult to quantify, like the cultural value of particular places. And these are things that are difficult to enter, like to, input in a model. But if you get people, communities telling you like this area is really important because of cultural or religious values, then these are things that should be incorporated in the model. And ideally they will.
Yeah, absolutely. I guess it'll also be interesting to see like the way you have it set up, the community involvement is like a second fine-tuning step. But I wonder if things like what you just mentioned might um, drive you to move that input earlier. You know what I mean?
Yes, that's possible too. Like the two things could happen like in cycles, so you can go back and forth between the two
Mhm.
optimization steps, ideally. Yeah.
Right, nice. All right, so I have a question for you from Taratra. Tarata says, they're joining from Madagascar and have a question about the environmental simulation part of it. How does the model account for human demographics and expansion, and how are species interactions such as prey-predator dynamics represented? And given your past research on Madagascar's endangered tree species, this is particularly interesting to Taratra.
Yes, so it's a good question. In the case of this Madagascar example, at least the one we included in our paper was a very simplistic simulation where where we didn't have the temporal component of, for example, demographic expansion. Um, and that was because we wanted to compare, to benchmark essentially Captain against an alternative approach that they didn't use this type of data. Ideally, if we have projections of changes in, for example, land use over time and population expansion, which are linked, of course, over time, this can be used in the simulation. Like one way this can be used in a simulation is by changing over time the disturbance level and the distribution of kind of anthropogenic pressure on the ecosystem in space and time, and this will affect where species can or not live. For example, if we expect entire chunks of forest to be cleared, we can input that in the model, and this will affect the distribution of trees, for instance. As for species interaction, this is currently very simple in the sense that we just have like some sort of carrying capacity that allows only a certain number of individuals to be in a given cell. So we don't have prey-predator interactions explicitly modeled. Although these in principle can be added to the simulation. It's like extra layers that could be added. Of course, when you think of like ecosystems of like 1,000 species, then it becomes difficult to actually represent the trophic interactions and all the ecological interactions among species, even because partly because we don't even know them. But in principle, this type of information can be included in the model.
Okay. Yeah, I had a similar question. One of the things that I, makes excites me about your work is the involvement of socioeconomic and demographic data. Um, and one of the questions I had was similar, which was about those kinds of like interactions. So, um, could you say more about where, like, in the work you presented, often when you're looking at future scenarios, it sounds like you're doing like prediction somewhere else, and then you're using like for climate change, right? You're using some climate change models to predict what the future scenarios would look like. Where in the model do you do a more like dynamic uh, interactions where the with one step in the model changes the inputs for the next step,
Yes. Yeah, so this happens continuously. Like, for example, if you change, so you have climate change will not affect per se the distribution of species. It will only affect the habitat suitability, which is like where can the species live in theory, right? In principle. But if there is like, for example, in the case of New Zealand, if there is like intense fishing activity in some area, maybe this area becomes available to a species, but the species will not make it there because of this activity. So this fishing pressure, for example. But if you remove the fishing pressure because the algorithm decided to put a conserved area uh, there, then the species will be able, if climate allows, they will be, and if their migration ability allows, they will be able to recolonize or colonize for the first time this area. And so this will contribute to making a species, for example, going from endangered to not endangered, because now maybe it has more areas where it can live and grow. So these type of interactions, or similarly, in the case of New Zealand, we have not only the fishing pressure for today, but also a projection of what the fishing pressure will look like in 70 years from now. And so we can make actually fishing pressure evolve over time as a function of these predictions that were made aside from Captain. And then we can use them to, and they will affect where the species actually occur, how abundant they will be, and so on. So this is all interlinked, and the conservation happens at the same time as these other things change: climate, disturbances, species moving around through dispersal and migration, things like this. So it's all
Hmm.
interlinked somehow.
Yeah, so on that, last part with the fishing pressure, you could imagine that your fishing pressure inputs are affected by the outputs of your model itself, right? Like as maybe the fishing pressure will change, as your model evolves. I wonder if there's a way to like capture, I don't know, the impact of adding that kind of complexity, right? Because you can keep adding complexity like that, right? You could like keep adding more sort of simulations within your simulation. And I wonder if there's a way to evaluate the efficacy of doing that kind of work.
Yeah. Yeah. So one of the things that can happen in principle, although we haven't really explored it yet in details, but it's like if you establish protected areas, you can have, for example, spillover effect, which is
Yeah.
like nature is recovering really well within this area, and then there is spillover, like these populations spreading outside of the protected area, which is beneficial for fishing actually, because fishing doesn't happen within the area, but it can happen around it. And fishing can actually benefit from having a protected area from which there is this spillover effects. And this, in principle, can be modeled and can be included in the simulation.
Yeah. Nice. Okay, great. Thank you. Yeah, I have a question from Salah. Uh, Salah asks, well, okay, specifically about the hexagonal shape that you're using for the decision units, but then asks, is there an effect of the size of the decision units? And I think this is a question about scale. Like when you're running your simulations, how does the scale of the potential um, actions affect the analysis?
Yes, yeah. So that's a good point. Um, the size of these protection units can be, in principle, arbitrary, but of course, it has to be designed in a way that makes sense. And this partly reflects the nature of the biodiversity system that you're looking at. Like, of course, if you are considering as your target species large mammals, which have a very wide geographic range. Each individual has a very wide geographic range. So then the units will have to account for this. Um, these species, they are very charismatic, but they usually represent the minority of the species in an ecosystem. So if you look at the majority of species, they will have a very narrow range, and most of them will not even move, like plants, fungi, and most invertebrates. They will have some dispersal ability, but they will not need a lot of area. So the scale depends a little bit on what you are kind of optimizing for. We do have in this multi-objective optimization, we can account, for example, for connectivity. So we can reward connectivity of areas um, explicitly, which will tend to create, even if you have a very fine-grained analysis with small protection units, you will still favor solutions where these units are connected in the end because they allow for connectivity. And these connectivity rewards can be designed, for example, to favor the establishment of larger areas that are beneficial for species that require a large continuous protected area. So it's a little bit dependent on the context and the biodiversity or the organisms really that you are looking at. But yeah, so in principle, the system works regardless, and then it's more like a scientific question of what makes most sense for the specific context.
Okay, great. Thanks. We are almost up. I'll end with a question from Jennifer, um, which is, I think, an interesting way to close out. Jennifer says, great work. I come from the perspective that all the benchmarking and comparisons of tool performance, like MarkSand, Zonation, Captain, tools like that, yours, is less impactful than how we can align on capacity to help the world start to use any of the tools in planning. So, for example, in Ghana, New Zealand, etc., are there ongoing SCP plans being developed with different organizations, governments, communities? How do we ensure we're not competing for the limited attention and capacity of governments with our desire to see our tools taken up?
Mm. Yeah, so um, yeah, the way we are trying to deal with this is by establishing collaborations whenever possible, applying for grants from governments to they will help implementing these tools in like real world scenarios. I think like at the end of the day, you need a software that is usable, that is powerful, but also like somewhat not yeah, like available for use like by a broader community. Um, I think there is still a scientific value, but also in general a value of like comparing different softwares and different tools because maybe if you run multiple optimizations across a wide range of tools, if they agree, then like you can be really confident that this is the solution. If they disagree, you can try to find out why they do and what may be better from one solution versus another one. So I think there is still a value in like comparing these different policies, then implementing them like in the real world, we need really, and this is something we are starting to establish and we hope to reinforce in the future. Really, we need an interaction between scientists and policymakers and like people who will actually be involved in the deployment of these policies. So, of course, as a computer scientist, I mostly work on the implementation of the software part, but then like we need and we are starting to increasingly interact with the people who will actually implement the policies themselves. Yeah.
Yeah. Yeah, it's a interesting question. One of the things that I think about a fair amount is sort of scientific workflow systems where, like one tool to try out various ones to come up with a general recommendation, kind of like what you're suggesting. I think I that's a good area for I think some more work and good collaborations.
Mm. Yeah, I think so. Yeah, hopefully. Yeah.
All right. Well, thank you very much, Danielle. This is great, and thanks for all your work on Captain. It's amazing, and I definitely look forward to seeing how the bottom up reinforcement learning works out. And thank you for joining us.
Right.
Thank you
Thank you very
to
much.
everybody for joining us and your great questions. The biodiversity series will continue. We have a few more sessions. The next one is in 2 weeks, September 29th. And then it's Ben Weinstein, who's going to be talking about open models, and that will be hosted by Lily Shu. So thanks again, Daniele, and thanks for everybody for joining us. Great to see you all.
Thank you very much. Bye.
Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.